Hello, quick video on vectors and what's called the scalar product, which is an extremely useful little tool for working with vectors in 2D and 3D. In the last video we looked at the equation for a line and vectors, and we talked about finding the closest point between a point and a line, and we can use the scalar product to help us with this, and particularly also for finding angles here between two vectors. That's particularly useful, and for finding vectors that are perpendicular, orthogonal. And in here, when two lines in 3D, we might actually need to find a vector that's perpendicular to the two line vectors. So that's what our scalar product helps us with. Often also called the dot product because we write it with a dot between the two. So let me take you through what that's about. Okay, the dot product of two vectors is written like that: a dot b, the scalar product. What we do is we multiply the x values together of the two vectors, and we multiply the y values together. So if I have two vectors, as I have here, my yellow vector, the A here is 4, 2, and the B vector is 1, 3. And if I want to find the dot product of those two, then I multiply my 4 and 1 together, gives me 4, and I multiply my 2 and 3 together, that gives me 6, and then I add them and I get 10. And I do exactly the same thing if I was interested in doing this in 3D, except I multiply my x's, my y's and my z's together and add them together. There we go. That doesn't seem to be a particularly useful thing at this point, does it? But actually it's going to prove to be extremely useful. And the reason is it helps us find out what the angle is between two vectors, and that's really useful. So here's a simple example of why that works. So here's two vectors. My yellow vector A is going to be going to the point cos theta sine theta. Yeah. So here's my, if I drew my little right angle triangle here, the base is going to be it's going to be cos theta. I've made the length 1 for now, so if that length is 1, then the base is going to be cos theta and the vertical height is going to be sine theta. Yeah. And if I just stick with a very simple idea that my B vector is just going to 1, 0. Yeah, it's just going along here to 1, 0. Well, what happens when I do the dot product of these two vectors? I've got my cos theta sine theta vector dot product with my 1, 0 vector. So what do? I multiply the top two together, my x value. So I get cos theta times 1, and then I multiply my y vector components together. That's sine theta times 0. And of course I'm going to add them. In this case, sine theta times 0 is 0, and so I'm just left with my first term, which is cos theta times 1 is cos theta, which is extremely useful because if I was multiplying two unit vectors together, then my dot product would actually be the cos of the angle. And if I let's extend that now, by rather than having unit vectors, let's make my A vector length A. So, but with the same direction. So I've got my x is a cos theta, my y is a sine theta. And then for my B vector, let's make the magnitude, again the length, scalar length of B. So it's now, rather than being 1, 0, it's now B, 0. And if I multiply those together, use a dot product, then I end up with my A cos theta times B. And then I'm adding to it my a sine theta times 0. So again, the second term is 0, and I'm just left with this first term, which is AB cos theta. So A and B are my magnitudes of my two vectors, and cos theta is the angle between them. So therefore I've now got a generalized formula, and this is true, you can try it in as many ways as you like, that a scalar product of A and B, A dot B, is the magnitude of A times the magnitude of B times the cosine of the angle between them. So therefore, if I work backwards, I can just multiply my scalar product, my two vectors together, A dot B. I can then work out my two magnitudes, a modulus of A, modulus of B, and then divide them through, and I can work out with my inverse cos function on my calculator, I can find the angle between two vectors. That's particularly useful in all of this stuff, isn't it? Because that works in 2D or 3D. So we can find the angle between two 3D vectors by just finding our scalar product, finding their lengths, and then finding the inverse cos, using the inverse cos to find our angle theta. Extremely useful. And of course, if these two vectors are parallel, then the angle between them is going to be 0, so cos theta is going to be 1. But more importantly, if the angle between them is 90 degrees, then cos theta is going to be 0. So we now have a method of checking that two vectors are perpendicular, or the other word for that is orthogonal, by multiplying them together. And if the dot product is 0, then the angle between them must be 90 degrees. Extremely useful, speeds up lots of stuff, and we'll use it for the example that we looked at earlier. So we had a look at this example in the previous video. I've got my line here, here's my line equation, and then I've got a point 1,5 here. And what I want to do is find the distance, the distance that that point is away from the line. So what am I interested in? Well, the vector that I'm going to create here is going to be at right angles to this vector, the main line vector, isn't it? And therefore, if I did the dot product of this vector here, the p minus n, yeah, that's p from n, and I do the dot product with the a vector, which is that vector there, we can see these are at right angles. Therefore, the dot product of those two, p minus n, scalar product or dot product, a, is going to equal 0, because I know they're at right angles, yeah? So if I want to find this point n, I need to find the right value of this point of n. N is going to be our xy. I need to find the right value of t to make this equation 0. So let's go on and do that, shall we? Okay, so I need to calculate what my vector p minus n is. Well, we know what the p value is. We were told that was 1,5. We know what the equation of the line was. That's this bit here. That's going to be our x value. In this case, I'm going to call it n because that's the point vector that I want. So that's, as we saw above here, there we go, there's our equation, isn't it? 2, 3 plus t lots of 2, 1. Yeah, and I'm taking that away. And when I do the scalar product, the dot product with 2, 1, because that's the a vector, that's our a vector, isn't it? Our line vector. That's the one going parallel to the line. When I dot product that, I'm going to get 0. Okay, sorry if I'm saying dot product a lot. You'll hear a load of mathematicians, once they've written it down as a scalar product, will keep referring to it as a dot product, because the way it's written. So our next line, therefore, is if I just tidy up these two here, two vectors there, I end up with the vector minus 1 and 2, and I've got my minus t lots of 2, 1, and that's going to be my dot product with 2, 1. You'll probably have seen already in your own mind that we can split this bracket up and do the calculation separately, so I can get this vector and dot product it with 2, 1, and I could do that one and do it. You could do it that way, or what I'm going to do here is I'm going to take my x value, there's my x value, that's going to be -1 minus 2 lots of t, and that's going to be multiplied by 2. And secondly, I've got my y value here, that's 2 minus t, and I'm going to multiply that by 1, and that's my dot product, and that's going to be equal to 0. But if I tidy up the left hand side here again, I end up with 4t. I've got 4t there, so it should be minus 5t there, shouldn't it? There's minus 4t there, and there's minus 1t there, but my units cancel out, don't they? I've got a minus 2 here and a plus 2 there, so I end up with 0. So therefore t equals 0. Yeah, that's what we were expecting. That's what we saw in my last video. If I substitute t equals 0 back into the line equation here, I've got the coordinates of the nearest point. That's what the n was, isn't it? It's our nearest point. So that's 2, 3 plus 0, lots of 2, 1, our line vector. So we're at 2, 3. That's what we would expect, isn't it? That's going back up here. That's our point there. That's our nearest point, is at 2, 3. And then, as I've done before, we could then find using Pythagoras, the distance from point 1, 5 to the point 2, 3. And using Pythagoras here in 2D, I've got our hypotenuse squared is the difference in our x's, the differences in our y's, both squared and then summed together. So our distance is the square root of 5. So that's extremely useful, isn't it? Because it saved us having to do simultaneous equations and having two variables, etc. We just created the dot product and we solved for t, our parameter in the line vector. Okay, and we can do the same sort of thing with two lines in 3 dimensions. Of course, two lines don't necessarily meet in 3 dimensions, and most of the time they don't meet. What we might be interested in is finding the closest point, the shortest distance between the two lines. That means finding the two closest points here, which I'm going to call N1 and N2. Excuse me, that just wrote over them, didn't really help. So if I find my two closest points, then the vector that goes between them here, which I'm going to call N, see this vector here. The important thing about that vector is it must be perpendicular to the yellow line vector and the red line vector. Yeah, so effectively these 3 lines are all perpendicular to each other, and in 3D we refer to this, you'll hear most people referring to lines as being orthogonal. Yeah, and if you've got a set of axes, x, y and z axes, they're all at right angles to each other, they're called orthogonal axes. Okay, so how am I going to go about finding the nearest point? Well, I've got my 2 line equations here. There's one for the yellow line, here's the one for the red one, and what we do know is that our vector here, our vector n, and must be at right angles to each of those, orthogonal to both of those. So if I find the dot product, the scalar product of that with the line vector, they must be 0. Yeah. So let's say that these points here are 2 nearest points when I've got parameter t and u, and that will be, so this one here will be n1. That's going to be point n1. This one's going to be n2. Yeah, they're the 2 nearest points. Well, therefore, the vector n1 minus n2, yeah, that's going to be our vector n, the vector that goes between the 2. And as we've discussed and looking at our diagram, we know that that vector must be at right angles to both the A1 vector, the line vector for A1, and the A2 line vector. Yeah. Sometimes you'll see people writing this sort of symbol. It's quite a nice shorthand, isn't it, to show that one's at right angles to the other or perpendicular. So the 2 dot products, the scalar products, must be 0. Yeah. So therefore, our n vector scalar product or dot product with A1 has got to be 0, and again our n vector dot product with A2 has got to be 0. Yeah, and we've got a formula for n. We've got our yellow line formula and subtract our red line formula. And if we just want to sort out our constants components here, we can take the first vector of this point and that point there and take one away from the other because subtraction, and we end up with this -7 plus 3 minus 1 vector. And then we've got our t line, our yellow line vector with its parameter t, take away our red line vector with its parameter u. Okay, and we can then go through, and for the left hand side I'll just run our way through it. We're going to calculate what n dot product A is going to be, and in effect here what we can do is we can split that up. So n dot A1 is going to be the same as looking at the line, this equation here above. I'm going to use it there. I can do a calculation of n dot this first vector, our constants vector dot A1, plus t lots of our yellow line vector dot A1, and finally our red line vector dot A1, and I can do those, and that's going to be equivalent, that's going to be equal to n dot A1 on the left hand side. So what I've done is then I can do these three calculations separately. So let's just do those, and I've put them down here on the A1 side on the left hand side. So here we go. So this is our constant dot A1, and our dot product is minus 14 plus 3. Yeah, there's our minus 14. There it comes. So I'm just going to do one to show you. So the first one's going to be minus 7 times 2 is minus 14. Here's our 3 times 1 is 3, and here's our minus 1 times 3, that's minus 3, so that lot totals minus 14. And I can go through now and do my yellow vector dotted with itself, line vector dotted with itself. You can see how it turns itself into, you get each of these values squared. Yeah, so it's 4, 2 and 9. So if you look at that, that's actually the length of that vector squared, isn't it? Looking at a 3D Pythag there, so I've got 14 for that. And then if I dot product these two vectors together, the line vectors A1 and A2, the red and the yellow, I end up with 2 plus 1 minus 3. I end up with 0, because these two vectors are actually at right angles. I've chosen two lines where the line vectors are at right angles for this example. And then I can substitute those values into our formula for n dot A1 equals 0. So there's our constant, minus 14, then we've got 14 lots of t, and we've got 0 lots of u, and that must equal 0. So tidying that up, I've got 14t equals 14, therefore t equals 1. Okay, so I now know what my t value is, and I can find our point for the nearest point on my yellow line by substituting in t1 into the line equation. So there's our starting point, and there's our one lot of the line vector. So I get the point, the nearest point for n1 is 2, 3, 1. And I can follow exactly the same approach on the right hand side here, looking at my red line, and the n dot A2 must equal 0. You know, those two vectors must be at right angles. So doing the same calculations, I get my 3 coefficients to put into my n dot A2 equals 0, and that leaves us with the equation. There's my minus 3 plus 0 lots of t minus 3 lots of u equals 0, and if we tidy that up, we end up with u equals minus 1. So our parameter on the red line is minus 1. Substitute that into the line equation, and there it is. There's our minus 1 going in there into the line equation. There's our two vectors, our point vector and our line vector, and we end up with our second point, which is that n2 is 6 minus 2, 0. So I now know the two nearest points, and I did that by finding the dot product and then finding the parameters. And once I know my 2 points, I can use these 2 points now, and using 3D Pythag, can't I? That the distance between those 2 points, where it's the difference in the x values plus the squared plus the difference in the y values squared plus the difference in the z values all squared. There we go. So I've got 4 squared plus 5 squared plus 1 squared, which I believe that d therefore equals the square root of 42. So there we are. We've shown how we can use the scalar product to help us find the nearest point of 2 lines. That's about as difficult as you're going to get in any of these exams. So here's a summary then. The scalar product, or dot product, after the way it's written, we just multiply each of the x values together, each of the y values, each of the z values, and then we sum them. It has a very useful characteristic in that the dot product of 2 vectors is the 2 magnitudes multiplied by cos, where cos of theta, where the angle theta is the angle between the 2 vectors, so we can find the angle between any 3D vectors using that. And if we want to find the closest point, then we're interested in points where perpendicular vectors, and therefore we're interested in the point where the angle between these vectors is 90 degrees, which has the benefit that cos theta equals 0. So in any of these calculations, our dot product between 2 vectors that are perpendicular or orthogonal are 0, and we can use that quite a lot. Quite a long video, but we got through an awful lot in that. I hope that's of use to you.